This is Glencoe Accelerated Math, Lesson 9-4, on direct variation. Direct variation is actually something that we have done before, but we called it something different. When we studied proportions, we said that there was such a thing as the constant of proportionality, and if something was proportional, then certain conditions had to be met. Does anybody remember what those conditions were?
No.
If a graph was proportional, what were those three things? Yes, ma'am. It had to start at the origin. What else?
It had to be a straight line.
Had to be a straight line. What was the third?
Increasing.
It had to be increasing. And when all those things took place, that meant that it had a unit rate, which meant that it had a constant of proportionality, which we called the slope. Correct?
Yes.
Okay. If something is an example of direct variation, it will pass through the origin, and it will be a straight line. The differences this time are that it may be decreasing, so it could be negative. And it doesn't start at the origin, but it passes through the origin, so we can use all four quadrants. Okay? That also means that it will have, if it is increasing, it will have a unit rate. So no matter what, it will have a slope. However, if it's decreasing instead of increasing, our unit rate would be found on the negative side, and it would be negative. Okay? So all of those things are true. We know how to do this. We're just looking at it in more than one quadrant. Okay? And a lot of times we will ask if something is direct variation. Now, if something relates directly to something else, then that means that we could multiply some value by something to get the answer. If we multiply some quantity by 3, that means that my constant of proportionality, which is my, how did I call it in this chapter? My constant of variation, which is the slope. Remember, all those things mean the same thing. Alright? You multiply by 3, that's that constant of variation. Can you multiply by 3 and then add 2 and call that a constant of variation?
No.
No, because the plus 2 part's going to screw you up every time, isn't it?
Mm-hmm.
Okay? So that also means that if we were going to write this as an equation, we should have a nice, easy equation because we'd have y equals some number times x. There's extra bits left on. Can it be direct variation?
No.
No, because that also means that it would not pass through the origin when graphed. Alright? So, let's look at example 1. In example 1, we have a picture of a graph. There we go. And in my graph, it shows that the cost of different amounts of trail mix. The cost is based on weight. So, we have to determine if the relationship is direct variation. So first of all, our graph has 3 different points labeled. What are those 3 points? Yes, ma'am.
$14.04,
Okay.
$28.08, and $42.12.
Okay. There's 2 different ways that we can figure this out. Option 1 says we can simplify our fractions. Do they all simplify to the same thing?
Yes. Yeah.
If I take 4 times 2, do I get 8?
Yes.
If I take 14 times 2, do I get 28? So then are they equivalent fractions?
Yes.
Okay. If I take 4 times 3, do I get 12?
Yes.
Guess what 14 times 3 is?
42.
42. So we know that they are equivalent to each other because the fractions are equivalent. Alright, so that means that we have a unit rate. We have a constant of variation. Now what they're asking us to do is to find that constant of variation. So how would I find the constant of variation? What do you think we would do?
Divide.
Divide. 14 divided by 4. How many times does 4 go into 14?
3.
3. 3 times 4 is?
12.
Subtract and I get?
2.
Alright? Because we're talking about money, I'm going to add a decimal point. How many times does 4 go into 20?
5.
5 times 4 is?
0. 20.
20. I subtract and I get?
0.
Okay. If we're talking about money, how many decimal places do I need?
2.
2. So that means that we're paying $3.50 per pound of trail mix. Okay, but when you do that, you're not getting a pound's worth of food. I'm not saying that this is the most cost-effective way. I'm saying that based on the place where this trail mix is purchased, this is the price per pound. Okay. What? Yes. All right. So when those things are met, is it proportional? Is it direct variation? If something is proportional, does that make it direct variation?
I don't know.
What do you think?
Maybe.
If something is proportional, is it an example of direct variation?
I mean, yeah.
Yeah.
Because it goes on the place. Wait. You know?
No.
Direct.
Alright, so we just said that this was an example of direct variation, correct?
Yeah.
Okay. The graph that we were given, does that graph show a proportional graph?
Yes.
Yeah, it meets the 3 conditions, correct?
Yes. Bless you.
So then can we say that situations that are proportional are also direct variation?
Yes.
Yeah. Buy a new one. Was gonna roll me. We're gonna get our math done today. Alright. Look at example 2, please. Example 2. If we have the equation y equals 40x, where y represents the distance in miles and x represents the number of hours, determine whether there is a constant of variation. If so, explain what it means. Alright, so we said that being proportional and being an example of direct variation were similar, correct?
Yeah.
Okay. But our direct variation can involve our negative components, correct?
Yes.
Okay, does anybody remember how did we set up our equation if something was proportional?
I don't remember.
Does anybody remember?
Fractions.
We didn't use a fraction.
Use a decimal.
No. So, let me remind you. If something was proportional, we said that it fit the format of the equation, y equals kx. Is that constant of proportionality?
That's the C.
You're right, but
C's don't look that good.
actually it's because the person who discovered it was
Named Karen.
German, and in German, that hard C sound is the letter K. Alright, so when we were looking at our constant of proportionality, we'd set things up as y equals kx. Well, we're not working in the land of proportions anymore, are we? Okay? Right now we're working in the land of functions. And guess what we call... You guys thought K for constant of proportionality was funny? You're going to love it when I give you the representation for slope. You ready?
Oh, yeah. Is it D? What is the M?
M represents the slope, which is the constant of variation, which is the constant of proportionality, which is the unit rate, which is the constant rate of change.
But where's the M? None of those words have M's.
And that is why I have no answer to why we use the variable m for the slope.
Made that.
Shh. Because it says to is probably the best answer I've got.
Minnie Mouse.
Ladies and gentlemen. So, we are going to transition to this format, y equals mx. We're going to add a b to that later, but I'll explain that later.
A B?
A b is in boy.
Oh.
A B as in.
What's that word that doesn't start with that letter I?
B as in bubbles.
The b actually represents your y-intercept.
Why?
I have no idea why they chose b. Here we go. Here we go. Hold up. So, if our equation is written in the form y equals mx, or y equals some number times x, is that direct variation? Yes, because it's written in that format, there's no extra pieces anywhere. So yes, that is direct variation. What was your question? Which part?
I mean, can't we just say that every 40 miles is equals 1 hour?
Right, so what we're saying is that for each hour traveled, we will go 40 miles, which is a unit rate, which is the same as a constant rate of change, which is constant of proportionality, which is the constant of variation, which we call the slope, which we are transitioning into writing as the variable m. And why we chose m, we're still not quite sure. So,
Why can't we just change it?
because that variable m is universal.
Yeah, just tell them.
When you get your doctorate in mathematics, then you may do that. Until that point, we're going to call it m. Okay?
I'll go home and start working on it.
You're going to go home and start working on it? Sounds fantastic. Alright. Listen up, please. Wait just a minute. Alright. Before we move on, I would like for us to look at example 4 on page 407. That's on comparing direct variations. And that's really important because most of the time that's when we're going to use this. I told you guys a story that when my husband and I were comparing cell phone plans, we looked at Verizon and we looked at Sprint and we looked at AT&T and we looked at how much it was going to cost for the phone plus the basic standard plan plus the data plus any discounts that we received based on where we worked. And I decided that to figure out which plan made the most sense, I was going to create equations for each line and I was going to graph them to compare them. Alright?
Actually did that?
Yes. Does that make me a loser? Probably. Yes. Did I end up saving our family over $200 over the next 18 months? Yes. So, are you going to do this for every situation? Not necessarily. But if you're comparing different cell phone plans, I would recommend doing it. It can save you a lot of money. If you are looking, there's a lot of different, situations, not necessarily in your, preteen, teenager life, but once you become an adult and have to make big people adult decisions when you're living that adulting life, you do have to make those kinds of decisions. And if you remember this, you probably will end up saving yourself a good amount of money.
That can't be kids.
At this point, yes, do I realize that I was being a major, loser doing algebra to figure out which cell phone plan that made the most sense? Yes, I pulled out my Excel spreadsheets and created the formulas and had it graphed for me. But you know what? But you know what?
You figured something out.
You just search on YouTube which one's better.
Yeah, you can look at that.
Excuse me. Because of our, you know, Google can provide you with a lot of information, but Google can't compare like that. It can tell you which will be the most expensive up front. But sometimes being more expensive up front saves you more money in the long run. Okay? That's where creating the equations and graphing them is a benefit.
I feel like you're one of few.
And I'm one of few that made the right decision and saved a whole bunch of money. Yes.
Which one did you choose?
We actually ended up with AT&T. Because so Sprint wasn't going to be the most cost-effective option until we had been on the plans for 32 months. And most phones don't, you know, nowadays with all the updates and stuff, you run out of storage on your phone before that point. Verizon was cheaper when you bought your phone outright at the beginning of the plan until month 13, and then AT&T became cheaper from months 13. It was more cost effective at the end of 2 years to go with AT&T.
So you went to all of them?
So I went to all of them. I got the information. And then after I got all the pricing information, I figured out which one we were going to go with.
Was your husband happy that you did that?
Oh, my husband thought I was a, loser for doing it too. But then when I showed him the graphs, he said, "Oh, that makes sense." Yes, ma'am. Good for you. All right. So, ladies and gentlemen, we've had some good discussion on why we might want to do this. Let's see what it actually looks like. All right. If we have an example 4, we're comparing the rate, we're comparing the heart rate of cats to dogs. Alright? So we have an equation for the number of heartbeats for a dog. Y equals 1.5x.
That's for which one?
That is for the dog.
The dog.
Okay? This is dog.
Oh, I could have read that.
We are given a graph. Ladies and gentlemen, this is the end of what we've got to do today. Stay with me. Now, can heart rate be negative?
No. Not.
No. You can't have negative time. You can't have a negative number of beats. Okay? If you're at 0, 0, then you're dead.
Yeah.
So, you can't have, or if you have a time and your heart rate is 0, you'd be dead. So, shh. So it can't be negative. For our cat, okay. For our cat, we have the points 1, 2, 2, 4,
3, 6.
3, 6,
4, 8.
4, 8. Alright.
Straight line.
So, that's our cat. If we're going to graph in the same plane, so in the same graph, I'm going to graph the function y equals 1.5x. That means when x is 1, y is 1.5. That doesn't work real well, does it? So instead I'm going to go with the 0.23. And I'm going to go with 4/6. And 6/9. Okay? In this situation, which one is faster?
The
cat.
Because it's smaller.
Not necessarily.
It runs because
So, because the line for the heartbeat of the cat lies above the line for the heart rate of the dog, that means it goes faster. Okay? Now, here's the other thing. Alright? We can also take the graph that we're given and put that into the form of an equation. So if we take 2 divided by 1, and we find the slope, 2 divided by 1 is 2. And 4 divided by 2 is 2. And 6 divided by 3 is 2. So how would we write our equation for the cat? Y equals 2x.
Yeah.
So if our slope is greater, that means that it's faster. Okay? Right. So when we are comparing, we can either put both into the form of an equation and compare the equations, or we can put both in the form of a graph and compare the graphs. Is one better than the other? Not really. When you're in direct variation, one is no better than the other. Okay? Any questions?
Yeah.